To define the next problem to be considered, recall that floor of x means the largest integer which is at most x. Problem 6 of this set of solved problems on continuous functions asks where the function f of x, which is defined by setting f of x is floor of x plus floor of negative of x, is continuous. We first observe that if x is not an integer, then it is between two integers. Therefore, if x is not an integer, then there is an integer n such that n minus 1 is less than x is less than n. And for this n, floor of x is n minus 1. Now, if n minus 1 is less than x is less than n, then negative n is less than negative of x is less than negative of n minus 1. Therefore, floor of negative of x is minus n. And this means that if x is not an integer, f of x is n minus 1 plus negative of n. It is minus 1. Therefore, all non-integer values of x, f of x is negative 1, and this also means that the limit of the function is everywhere negative 1, because arbitrarily close to integer points there are, of course, non-integer points. So the limit is everywhere negative 1. But if x is an integer point, then floor of x is x and floor of negative of x is also negative of x. So if x is integer, then f of x is 0. This means that the graph of f looks like this red curve. It takes the value negative 1 for all non-integer values of x, and then for integer values of x, the graph jumps to 0. And we conclude that f is continuous at all non-integer points and discontinuous at all integer points. In problem number 7, we have to study the continuity of the function f of x equals square root of 1 plus sine of x squared minus 1, and that divided by x squared. So we first have to figure out for which values of x this expression square root of 1 plus sine of x squared minus 1 divided by x squared is defined. First we observe that x squared and sine are continuous functions, therefore also sine of x squared is as a composition of two continuous functions, it is also continuous. And likewise 1 plus sine of x squared is continuous, and then we observe that 1 plus sine of x squared is never negative. This means that we can always take square root of it, and this means that square root of 1 plus sine of x squared is defined for all values of x, and it is continuous for all values of x. So the numerator, square root of 1 plus sine of x squared minus 1, is defined and continuous for all x. The denominator, x squared, is continuous and takes the value 0 only at x equals 0. So we conclude that this function f is defined and continuous for all non-zero values of x. If x equals 0, then of course x squared is also 0 and sine of that is 0. So if x equals 0, then this function f of x, the expression defining it, gets the value 0 divided by 0. This is not a number, therefore f is not defined for x equals 0. Here is the graph of the function f. It's a red curve. It seems that the function has a limit as x approaches 0, and if it has a limit, then we can extend the domain of definition of this function to 0 also in such a way that the function becomes continuous. So we have to find out whether f has a limit. The picture that you just saw seems to indicate that this is the case. In order to study the behavior of the function f near the point x equals 0, we have to multiply and divide the expression defining the function by the conjugate square root of square root expression. So we rewrite f of x is square root of 1 plus sine of x squared minus 1 times square root of 1 plus sine of x squared plus 1 divided by x squared times square root of 1 plus sine of x squared plus 1. Here the numerator, square root of 1 plus sine of x squared minus 1 times square root of 1 plus sine of x squared plus 1 simplifies to square root of 1 plus sine of x squared, and that square root squared minus 1 squared. So this becomes just sine of x squared, because square root of 1 plus sine of x squared is 1 plus sine of x squared, and then we have negative 1. So 1 and negative 1 cancel out, so f of x becomes sine of x squared divided by x squared times square root of 1 plus sine of x squared plus 1. But now sine of x squared divided by x squared has the limit 1 as x approaches 0. This is a fact that we have seen previously. 1 plus square root of 1 plus sine of x squared plus 1 approaches 1 divided by square root of 1 plus 1, that is 1 divided by 2 as x approaches 0. So we conclude that the limit of f as x approaches 0 is 1/2. So this means that if we set f at 0 to be 1/2, then f is continuous at x equals 0. In problem 8, we have to evaluate the limit as x approaches 1 of arcsine of 1 minus square root of x divided by 1 minus x. We start by looking at the argument of arcsine. 1 minus square root of x divided by 1 minus x takes the value 0 divided by 0 when x is 1. Therefore, we must perform a rewriting in order to understand what the limit might be. And the rewriting is that we multiply and divide by the conjugate square root expression. So we multiply and divide by 1 plus square root of x. So the expression 1 minus square root of x divided by 1 minus x becomes 1 minus square root of x times 1 plus square root of x divided by 1 minus x times 1 plus square root of x. 1 minus square root of x times 1 plus square root of x simplifies to just 1 minus x. So we get that the rewriting of the argument of arcsine in this function is 1 minus x divided by 1 minus x divided by times 1 plus square root of x. 1 minus x cancels out. So we get that this expression is really 1 divided by 1 plus square root of x. As x approaches 1, this has the limit 1/2. Now, we have to compute the limit of arcsine of this expression, and we observe that the domain of the function arcsine is the closed interval from -1 to 1. Arcsine is inverse function of the sine function. We have previously observed that inverse functions of trigonometric functions are continuous where they are defined. Therefore, arcsine is continuous, and it is certainly continuous at the point 1/2. Therefore, by the properties of continuous functions, limit as x approaches 1 of arcsine of 1 minus square root of x divided by 1 minus x is arcsine of the limit. So it is arcsine of limit as x approaches 1 minus square root of x divided by 1 minus x, and we already computed that this limit is 1/2, so we conclude that the limit that we have to compute here is arcsine of 1/2, which is pi over 6. In problem 9, we have to evaluate a limit as x approaches pi of sine of x plus sine of x. So here we observe that sine and the function x, they are of course both continuous functions and everywhere defined. So x plus sine of x is also continuous, and sine of x plus sine of x is also continuous. So we conclude that the function sine of x plus sine of x is continuous and defined for all values of x. By the properties of continuous functions, limit as x approaches pi of sine of x plus sine of x is same as sine of the limit of x plus sine of x as x approaches pi. And this is pi plus sine of pi, which is pi plus sine of pi is just pi, and we get that the limit is 0. In problem 10, we have to consider a piecewise defined function. We have to find the value of the constant c that makes the function f of x, which is defined by setting f of x is c times x squared plus 2x if x is less than 2, and x cubed minus c times x if x is greater than or equal to 2, and we have to figure out for which value of c this function is continuous. So to that end, we first observe that f is a polynomial function on the interval from negative infinity to 2. It is just cx squared plus 2x, and as such it is continuous. It is also a polynomial function x cubed minus c times x when x is greater than or equal to 2, so it is continuous for all those values as well. So it is continuous on this open interval from negative infinity to 2 and from 2 to the infinity. So we have to figure out whether the function can be made continuous at x equals 2. To that end, it must satisfy that the value of the function at that point x equals 2 is the limit of the function. So the limit must exist. And now this is piecewise defined, so we have to compute one-sided limits. First, we have to compute what is limit of f of x as x approaches 2 through numbers larger than 2 and then through numbers less than 2. From the definition of f, when we compute the limit of f of x as x approaches 2 through numbers larger than 2, we use the expression x cubed minus c times x for f. And therefore it is same as limit of x cubed minus c times x as x approaches 2, and this is 8 minus 2 times x, 2 times c. The left-hand limit is likewise the limit of the expression cx squared plus 2x when x approaches 2, and that is 4 times c plus 4. You get these results simply by plugging in the value x equals 2. Now, in order to have continuity, these two one-sided limits must agree. So f is continuous at x equals 2 if 8 minus 2c is 4c plus 4. This is an equation which is easy to solve. We get c equals 2 over 3. Problem 11 is slightly more complicated but of the same type as problem 10. We have to find the values of the constants a and b, which makes the function f of x, which is defined by setting f of x is x squared minus 4 and that divided by x minus 2 if x is less than 2, and then ax squared minus bx plus 3 if x is between 2 and 3, 2 allowed, 3 not, and 2x minus a plus b if x is greater than or equal to 3. Now, x squared minus 4 divided by x minus 2 is certainly continuous when x is less than 2, because then the denominator is not 0. A times x squared minus b times x plus 3 is also continuous for all values of x. Certainly it is continuous between 2 and 3. And 2x minus a plus b is likewise continuous for all values of x. So we observe that every piece of this function f, which is piecewise defined, every expression defining the function f is certainly continuous on the interval where it is being used. So f is continuous on the interval from negative infinity to 2, open interval, from 2 to 3, open interval, and then from 3 to the infinity, open interval again. In order to figure out for which values of a and b f might be continuous at 2 and at 3, we have to compute the one-sided limits. So we must have that f at 2 is the same as a limit as x approaches 2 through numbers larger than 2 of f of x, and that is the same as a limit as x approaches 2 through numbers less than 2 of f of x. And likewise, f at 3 must be a limit of f of x as x approaches 3 through numbers larger than 3, and that must be the same as a limit of f of x as x approaches 3 through numbers smaller than 3. These one-sided limits we compute by inserting the appropriate expressions for f in these limit computations. So from the definition of f, we conclude that the limit of f of x as x approaches 2 through numbers larger than 2 is same as the limit of ax squared minus bx plus 3 as x approaches 2. And this is simply computed by inserting x equals 2, so we get 4a minus 2b plus 3. And this is also the value of the function at 2. The limit of f of x as x approaches 2 from the negative side through numbers smaller than 2 is limit of x squared minus 4 divided by x minus 2 as x approaches 2. But the x squared minus 4 is x minus 2 times x plus 2. X minus 2 cancels out, so this is a limit as x approaches 2 of x plus 2, and this limit is 4. Simply insert x equals 2 in this expression. So we conclude that f is continuous at x equals 2 if these two one-sided limits agree, so if 4a minus 2b plus 3 equals 4. This is the first condition on a and b. We have two unknowns, and we are going to get two conditions, of which this is the first one. The second condition we get by studying f at x equals 3. So from the definition of f, f at 3 is limit as x approaches 3 through numbers larger than 3 of f of x, that is limit of 2x minus a plus b as x approaches 3, and this is 6 minus a plus b. And the limit as x approaches 3 through numbers smaller than 3 is the limit of ax squared minus bx plus 3 as x approaches 3. This is also computed simply by inserting x equals 3. We get 9a minus 3b plus 3. So we conclude f is continuous at x equals 3 if 6 minus a plus b equals 9a minus 3b plus 3. And this is the second condition. So now we have obtained two conditions, and we have two unknowns, and these two conditions simplify to 10a minus 4b equals 3 and 4a minus 2b equals 1. Now, to solve this set of equations, we multiply the second equation by 2, so it becomes 8a minus 4b equals 2. And then we subtract the second equation from the first one, so then minus 4b cancels out, and we get 2a equals 1, so a equals 1/2, and we also get 2 minus 2b equals 1 after inserting a equals 1/2 in the second equation. So solutions for these equations are a equals 1/2 and b equals 1/2. So for these values of a and b, the function f is continuous.